Okay, so hello everyone. Today I'll be talking about work I did during an internship with Yannick in Paris. And I'll be starting a PhD with him in September. So this work is about a survey of metaprogramming in proof assistance. Namely, we could survey ROC, Agda, and Lean. But we also think it would be interesting to extend this study to other proof assistants, such as Idris or Isabel or Beluga. So if you're interested, come and talk to us at the end of this talk or at the end of the session. We have a preprint online if you want to learn more. So proof assistants provide powerful automation. You can write your own tactics, implement macros, and the focus of this talk is about boilerplate generation. So you can mechanically generate functions and lemmas. A common archetype is to take as input an inductive and generate some functions based on this inductive. For instance, most proof assistants generate induction principles for you, but you can also write metaprograms to generate Boolean equality functions, printing functions, and so on. Now here an issue is that there is actually no consensus on how to do metaprogramming. There are many different metaprogramming frameworks. ROC even has 4 different ones. And while experts usually know the pros and cons of each framework, users aren't aware of these. So in this talk, we try to answer the question of how these frameworks compare. So we survey metaprogramming in ROC with 4 frameworks: OCaml plugins, MetaROC, LTAC2, and LP, and in Agda and in Lean. And we do this through a case study, which is deriving instances for a type class, the functor type class from functional programming. So this is the functor type class using ROC syntax, which I'm sure all of you are familiar with. And so what we were trying to do is to write a metaprogram which takes as input an inductive, here the simple option inductive, and generates the function on the right here automatically. So we write one implementation of this metaprogram in each framework and use these implementations to highlight some of the pros and cons of each framework. So I'll start with OCaml plugins. So OCaml plugins allow you to do metaprogramming for ROC by directly interfacing with ROC's implementation. So you can use plugins to define new commands and tactics. And plugins have access to all of the elaborator's features. You have access to unification, type inference, and so on. And also more low-level APIs, such as the ability to extend the parser and more. So a pro of OCaml is that it's a battle-tested programming language. It has many good libraries, a performant compiler, high-quality tools, and so on. But that's about it. OCaml is not particularly well-suited for metaprogramming. Some of the cons of OCaml are that you only have access to very low-level API to build terms. So here, const is the type of the ROC terms represented in OCaml. It's the AST. So like make app builds an application, make case builds a pattern matching. And as you can see from the signature of make case, you have to give lots of low-level details that usually ROC infers for you. You have to give implicit arguments, universe instances. You have to be very specific about dependent pattern matching information and so on. Another con of OCaml is that it uses unscoped De Bruijn indices. Your make_rel is a constructor for variables. So here I have an example of like this term, which is a lambda abstraction and returns a sum of f of x. Here is exactly sum of f of x built using De Bruijn indices. And as you can imagine, this is very error prone. And you have to, in general, you have to write lists and shifts by hand, which is hard to get right. Okay, so that was OCaml. Next, I'll speak a bit about MetaROC, which allows you to do metaprogramming for ROC directly in ROC. So metaprograms are simply ROC programs. And MetaROC exposes an inductive here, term, which is the term AST. So you have a constructor for variables, for application, lambda abstractions, and so on. And MetaROC also exposes bindings to the kernel and to the elaborator through a monad, the template monad here, which you can use to make new definitions or access the features of the elaborator. And then you can run programs from the template monad at the top level using a command. So a pro of MetaROC is that you have access to basic term quotations, which are a higher level API to build the AST of terms. So you have this function here, tmQuote, which takes an arbitrary ROC term and returns its AST. And then tm_unquote, which goes in the opposite direction. And using this, you don't have to give all the low-level details all the time. And a last pro of MetaRock is that you can do formal verification of your meta programs, at least in theory. So MetaRock includes a formalization of the meta theory of rock and verified implementation of the kernel, including, for instance, reduction functions, which you can use. But a crucial thing that's missing is that you don't have any specification for the operations which use the template monad. So as soon as you use interesting metaprogramming features, you can't prove anything anymore. Cons of MetaRock was that it uses De Bruijn indices unscoped, same as OCaml. And the term quotations, while they are useful, are still a bit basic because you can't quote terms with free variables. And in general, you would want something called quasi-quotations, where you can go back and forth between the rock syntax and the AST, but you don't have this. And lastly, programming in rock can be a bit difficult. For instance, it's hard to do input-output. Functions need to terminate by default. Working with exceptions can be a bit difficult. And this is mainly because rock doesn't really have a good monad library for programming. Then I'll speak a bit about Agda, which offers a very similar metaprogramming experience to MetaRock. So in Agda, metaprograms are simply Agda programs. And you can use functionality from the kernel and elaborator using a monad, the type checking monad TC here, which is the analog of MetaRock's template monad. You have term quotations using the same mechanism as MetaRock. And now a difference with MetaRock, and actually something that Agda does quite well, is that Agda handles the state of the prover. So the global environment, local context, and unification state. All of this is handled directly in the TC monad, which is kind of like a state monad. So you don't have to handle it explicitly. And Agda has good monad libraries to help with programming, so with exceptions and input-output. Cons of Agda are that it uses De Bruijn indices, unscoped. And the term representation is actually quite constrained. So terms are beta normal by construction, which means it's a bit tricky to build an application of one term to another. And it's also tricky to define a substitution function, and you don't have access to a substitution function by default in the metaprogramming library. Another limitation is that Agda inlines let bindings during elaboration, so metaprograms can't make use of these. And this has some consequences. For instance, you can't really use local typecast instances when doing Agda metaprogramming. Okay, so now I'll speak a bit about LTAC2. Which is mainly a tactic language for rock, but also offers some metaprogramming facilities. So using LTAC2, you can actually use tactics to build your terms. Here's a simple example. So I'm building this function map option, which maps over option types. And I can use simple tactics, such as intros or destruct to insert a pattern match to build this function. And this actually scales quite nicely to more complex metaprograms. Another pro of LTAC2 is that it manages the prover state imperatively. So you can query and modify the global environment and unification state without needing to do bookkeeping manually or to work in a monad. And lastly, LTAC2 also has basic term quotations, which are quite useful. Cons of LTAC2 is that tactics can be a bit difficult to reason about in the context of metaprogramming because they work on an implicit goal. So for instance, this function build map takes as input an inductive and builds a term of this type, which is the mapping function over the inductive I. And this is implicit in the code, but actually really crucial to understand the code. Then, while LTAC2 has a really nice tactic library, it also allows you to directly manipulate the AST of terms, similar to OCaml or to MetaRock. But this part of LTAC2 is quite weak. The term AST uses De Bruijn indices, and many standard functions to manipulate terms are missing. And lastly, LTAC2 misses some crucial metaprogramming features. For instance, you can't use LTAC2 to declare new constants or new commands. So LP is the last framework I'll talk about for rock. And it's so LP is a logic programming language based on Lambda Prolog. And a distinctive feature of LP is that it uses higher order abstract syntax for binders instead of De Bruijn indices. So for instance, here, fun is the constructor for lambda abstractions in the AST of LP terms. Yeah. And it takes as input the name of the binder, the type of the binder, and then the body of the lambda abstraction reuses LP functions. And in our experience, higher order abstract syntax is really nice to use in practice. You don't have all the downsides of De Bruijn indices. You don't have to do shifts, etc. Then LP has really powerful term quotations. So it not only does it have quotations using double brackets, so you can escape from LP syntax to rock syntax. You also have the opposite of operation, anti-quotations, where you can nest anti-quotations and quotations. This is really useful in practice. So here's an example of how this works. And lastly, LP manages the proof of state for you, similar to LTAC 2. Cons of LP is that it's a logic programming language, which is a big paradigm shift for users of proof assistance. And it has a steep learning curve, and some standard tricks can be unintuitive. And the language also has some unintuitive or missing language features. For instance, LP uses implicit backtracking, which is useful for proof search, but not so much for general metaprogramming. And like another example of limitation is the lack of structured representation for data, for instance, records. Like this is an example of a function I have in my code, which has a dozen arguments. And this is really common using LP. Okay, the last framework I'll talk about is Lean. So Lean's elaborator is mostly bootstrapped, implemented in Lean itself, which means that metaprograms are simply Lean programs and have access to the complete Lean implementation. Another pro of Lean is that it doesn't use De Bruijn indices. It uses a binder representation called locally nameless, which means that bound variables use De Bruijn indices and free variables use names. This is an example to build this function here, which abstracts over some variables and returns f of x. You can here declare each variable. And crucially, what you get here is a name, not a De Bruijn index. So you can build the application of f to x without needing De Bruijn indices. And then you can abstract over the variables to replace the names by De Bruijn indices. So although locally nameless uses De Bruijn indices internally, you never have to deal with shifts or with numbers as a user. Then Lean also has powerful term quotations, quotations and anti-quotations. And it has good effect handling using monads, notably the metaprogramming monad meta-m. And here a key difference with Agda and Metarock is that meta-m is actually implemented directly in Agda. It's simply a kind of reader state monad. So there's nothing really fancy going on here. Cons of Lean, and this is a big con, is that Lean elaborates fixed points and pattern matching to recursors. So this means that metaprograms can't make use of fixed points and pattern matching. You have to rely instead on recursors, which can get very complex for nested inductives. And for this reason, actually, our Lean implementation does not support inductives such as lists or trees. Okay, so now that we've seen the pros and cons of these frameworks, I'd like to draw a couple insights. So here is a big table of the pros and cons, of recurring issues we found with these frameworks. I don't expect you to read all of this. You can come to it later on if you want to decide on a framework. But the important observation here is that every framework has a bunch of red crosses. So it's really not solved yet. Then some ideal metaprogramming features we think a framework should have. So first, the choice of the term AST is actually quite important, whether you want something high level close to user syntax or something more lower level close to the kernel syntax. And especially binder representation is quite important. So unscoped De Bruijn indices are, of course, very difficult to use, and hosts and locally nameless are much nicer. Something that would be interesting would be to see how Idris compares with scoped De Bruijn indices, I think. Then term quotations and anti-quotations are very important, of course. And something that was surprising to me is that although metaprograms can seem as though they are pure transformations, for instance, here I'm taking as input an inductive and building a term, you actually want to make use of some effects along the way, both generic effects, such as printing, non-termination exceptions, and some domain-specific effects, such as manipulating the state of the proof assistant, like unification state and environment. And lastly, we think that verification of metaprograms can be desirable, not so much for users, because the output of a metaprogram is always rechecked by the kernel, but for developers of metaprograms. So future work is to extend this study to other proof assistance languages, or to other examples. So if you're interested, come and talk to us at the end of the talk. And then we want to develop a metaprogramming framework based on our insights, most likely by extending Metarock. And in particular, we want to focus on verified metaprogramming, for instance, using program logics and maybe separation logic to handle unification state. Okay, and that's it. You can go have a look at the code on GitHub if you're interested.